Hi everyone, in this video I'm going to be running my Statistical Analysis PySpark program for my single node big data virtual machine. Just a quick note, this video does contain a lot of biological terminology and concepts to do with DNA sequencing, therefore I highly recommend reviewing some background theory on the topic before continuing. The dataset that I will be manipulating contains a subset of DNA short-read sequences of length 250 characters from strains of chlamydia, which I've already extracted, transformed and cleansed from the original FASTQ file. This program reads in a series of short-read sequences and starts by analysing the composition of each short-read by generating a 3-mer frequency vector, which contains the frequency occurrence of each 3-mer possibility in the short-read, where a 3-mer is a substring of length 3. Taking this 3-mer frequency matrix developed, I will then perform a statistical analysis looking at the max, mean and variance of the percentage composition of each 3-mer possibility across all short reads. I will then be developing a Pearson's correlation matrix to see how each of the frequencies of all possibilities of 3-mers are correlated with each other. All the statistical summaries will then be visualized using Python's matplotlib. So I developed this PySpark program using a Jupyter notebook where the data was stored in a Hadoop distributed file system. I will be accessing the data via Hive and using Spark as my processing engine with Python as the programming interface. Now I'm going to take you through my code at a very high level. What I first did was set both the Spark and Hive contexts to allow me to interact with both these technologies from the Jupyter notebook. I then loaded in the DNA short-read sequences dataset from HDFS into Spark via Hive. I then generated a Python dictionary where each key was a possible 3-mer and the value is the occurrence, which I have currently set to 0, which I will be later incrementing on each occurrence within a short read. I also generated a list containing all possible 3-mer combinations, which will be used as my x-axis label when it comes to visualizing the statistical summaries later on in the program. The first step of generating the frequency matrix is to calculate all 3-mers or substrings of length 3 present in the short read. To do this, I created a window of size 3 which iterates over each short read and creates a new RDD where each entry is a list of all 248 substrings of length 3 found within the 250 character short read. To generate the frequency matrix, I can then create a new RDD where each entry is the 3-mer dictionary that we created earlier, where the key is the 3-mer and the value is the occurrence. We can then take the list that we just generated in the previous function and iterate through it. And for each 3-mer in the list, the corresponding dictionary value is then incremented by 1 on each occurrence. What we can then do is extract all the values from this dictionary and create a new RDD where each element is a list or vector of length 64 containing the occurrence of each possible 3-mer in the short read. Taking this frequency matrix that we have just generated, what I then did was write my results to a CSV file stored in HDFS, as I will be manipulating this 3-mer frequency matrix once again in challenge 4. I can then generate now my statistical summary. So using Spark's MLlib statistical library, what I can then do is build up a column-wise statistical summary of each possible 3-mer in the matrix. This function will return 3 64-length vectors corresponding to the max, mean and variance of each possible 3-mer in the matrix. Once the statistical summary is generated and returned, what I then did was create 3 functions which then visualize those results, looking at the mean, the max and the variance of each possible 3-mer in the frequency matrix. Once again, using Spark MLlib statistical library, what I can then do is calculate a Pearson's correlation coefficient matrix between all 64 possible 3mers in the frequency matrix, and then visualize the results in a correlation matrix of size 64 by 64, analyzing every single combination. Moving on to the main method now, what I can then do is start to call all the functions that are defined above. I can set the Spark and Hive context, load in the data, convert it to an RDD, extract the short read sequence. I can then filter out any short reads that contain the character N, as this represents that a specific base could not be identified. I can then generate the list with all possible 3mers present in a short read. I can then generate the frequency matrix, write my results to HDFS, calculate the statistical summaries, generate the visualizations using Python's matplotlib, and also calculate and plot the Pearson's correlation coefficient matrix between all 64 possible 3mers. What I'm now going to do is run the program, and we can see the outputs that it produces. So when I run this, I'm going to be asked for a few user inputted parameters. So first, would I like to enable debug mode? Nope. What it then does is set the Spark and Hive context. So once again, it will allow me to interact with both the technologies. And then I'll be asked again in a second, once both of them have been set, of the number of short reads that I like analyzed. So I'm going to enter 10,000. Now this program is going to take about a minute and a bit to run. So I'm just going to leave you guys for a second and I'll come back. Okay, so now the program has finished executing and has outputted all the results that we can now take a look at. So the first visual we're presented with shows a maximum percentage composition that is present across all short reads for each of the 3mers possibilities. So down at the bottom we have all 64 3mer possibilities and the maximum percentage composition that occurred across all short reads. So the two that really stand out is the 3mer AAA, where the max composition was around about 13%, and the 3mer TTT, the maximum percentage composition that occurred was around 19%. Moving on, we then have a very similar thing, but now this time looking at the mean percentage composition of each 3mer within the dataset. And once again, we can see that the 3mers AAA and TTT tend to have the largest percentage composition out of all the 3mers present. And then, as we can expect from using the above two visuals, that the variance now for the 3mers AAA and TTT are going to be far greater than all the rest, due to the fact that majority of the short reads contain quite a lot of quite a high percentage composition of those possible 3mers. Moving down, what we now have is the Pearson's correlation matrix, which analyzes all 64 possible 3mer frequency occurrences against each other. And what we can start seeing now is a few combinations that have very high positive correlation. We have some that have absolute no correlation, and we also have a few that have a very weak correlation. But something that stands out that is quite faint and hard to see is that you do have these unusual diagonal lines going across, showing that there is some trend in positive correlation going across. And finally, at the bottom, what we've done is presented with some performance stats. So the data loading took 22 seconds, data processing took 46 seconds. So in total, the 10,000 reviews were executed in 68.9 seconds.